380,000 years after the beginning, the universe exhales its last light. The fireball of creation has cooled to a dull orange glow, and space is still stretching, dragging every wavelength with it. Within a few million years, that glow slides from orange to red, then below red, into infrared no eye could ever catch. Then the dark, not dusk, not dimness, dark. In every direction, at every distance, nothing shines. No star, no galaxy, no ember of glowing gas. For roughly 100 million years longer than the entire reign of the mammals, start to finish, the universe emits no light at all. But gravity does not sleep. Cold hydrogen and helium drift together in the blackness, pooling inside invisible halos of dark matter, each one outweighing 1 million suns. The universe is assembling something it has never made before. It simply refuses to show its work. Halos merge and deepen. Gas gathers at their centers, cold and patient, warming only as it compresses. Nothing yet burns, nothing yet can. Silence, pressure, patience. Then, a point. A single spark of blue-white ignites in a darkness that has never once held light. One star, the first star. Everything after this moment descends from that ignition. Every galaxy, every world, every atom of iron and blood and calcium and bone, all of it begins here, with one small fire in an endless night. Because this is how the universe relights itself. Not all at once, but one star at a time. It hangs there, small and alone. Small, alone, enough. Honesty first. No one has ever seen a first star. Not one. Every claim in this episode comes from equations, from supercomputer simulations, from physics pushed hard into a place no telescope has reached. Start with the raw material. The early universe offers gas of brutal simplicity, about 76% hydrogen, 24% helium, a whisper of lithium, nothing heavier. No carbon, no oxygen, no iron. And that absence matters because heavy elements are how hot gas cools. Without them, cooling falls to fragile molecules of hydrogen, and they work slowly. So gravity gathers its gas gently into small, dark matter halos, 100,000 to 1 million times the mass of the sun, total. Small by cosmic standards. The Milky Way outweighs them 1 million times over. Inside, the gas collapses in one slow heap. No metals means no shattering into small pieces. The theorists' result? Monsters. Single stars of tens to hundreds of solar masses, around 100, perhaps up to 300. The comparison to our sun breaks down fast. A surface near 100,000 degrees, 17 times hotter than the sun's face. A 300 solar mass giant pours out the light of 5 million suns. And it lives fast. 2, maybe 3 million years. The sun gets 10 billion. The giant gets a 3,000th of that. Die young, die enormous. For scale, compress all 13.8 billion years into a single day. The afterglow fades about 40 seconds past midnight. The first stars ignite 10 to 20 minutes in. The dark ages are the day's first quarter hour. None of this is observed. Every mass, every temperature, every lifetime is a prediction published and waiting for an eye. Every monster star keeps the same appointment. Its mass chooses the manner of its death, and the menu has 3 entries. Below 140 suns, the ending is almost familiar. The core exhausts its fuel, collapses in a heartbeat, and the star detonates as a supernova, leaving a crushed cinder, a neutron core, sometimes a modest black hole behind. Between 140 and 260 solar masses, physics invents something stranger. Deep in the core, gamma rays begin converting into particle pairs, and pairs resist gravity far more weakly than light. Pressure fails. The collapse runs away in seconds. All at once, the star ignites and tears itself completely apart. No core, no black hole, no remnant of any kind. Above 260 suns, the giant skips the fireworks entirely and falls straight into a black hole of its own making. The death is silent, and it is total. The middle path is the one that changed everything. In one such death, a 200 solar mass star hurls tens of solar masses of brand new metals into the dark. The first carbon, oxygen, silicon, and iron the universe has ever owned. With a single blast, an entire mini-halo can be pushed past the critical metal line, roughly a 3,000th of the sun's content. Gas beyond that line cools faster, clumps smaller, and starts building ordinary stars. The giants, in other words, engineered their own extinction. Proportionally, each one lived a mayfly's single day against a redwood century's 2 million years set against the sun's 10 billion. The era ended itself. So if the monsters destroyed themselves this completely, what did they leave behind? Now the story runs into a wall. Webb keeps finding black holes that should not exist yet. The quasar J03131806 is the exhibit of record. At redshift 7.642, it burns with the appetite of a 1/6 billion solar mass black hole, fully grown when the universe was just 670 million years old. That is barely 5% of cosmic history, a full gray beard on a toddler. The arithmetic is the problem. Even fed as fast as physics allows, an ordinary stellar corpse of a few tens of solar masses cannot climb to 1 billion suns in the time available. The growth curve runs out of road. One elegant fix is to skip the lowest rungs. Above 260 solar masses, a star skips the explosion and collapses directly into a black hole of 10,000 to 100,000 suns. With seeds that heavy, the growth curve gets a generous head start. Webb may already have seen one. UHZ-1 sits at redshift 10.3. Its light magnified by the galaxy cluster Abell 2744, a black hole of 10 to 100 million solar masses, possibly rivaling its entire host galaxy in weight. On paper, it is precisely what a direct collapse seed should look like, though the X-ray evidence is sparse and the argument is alive. Nor is it alone. GN Z11 at redshift 10.6 feeds a black hole of 2 million suns, while Sears 1019 carries roughly 10 million at redshift 8.68. Then there are the little red dots, compact crimson specks scattered across redshifts 4 to 8, most likely faint dust-reddened quasars, though starbursts have not been ruled out. The monsters died young, their corpses may have founded an empire. Now we have to catch one. Strip every metal out of a star's gas, and its spectrum changes character. Freed from that shielding, a metal-free cluster burns hot enough to tear both electrons off helium, a feat ordinary starlight almost never manages. The TEL is a fierce helium line at 1,640 angstroms, towering hydrogen lines beside it, then silence where every metal line should sit. 3 features, 1 verdict. Faking that combination is nearly impossible. That is the smoking gun. A lone star will not do it, though we hunt entire clusters. 100,000 first stars burning as one beacon. Here is the catch. Distance, even a monster 200 times the sun's mass, lies beyond direct reach from 13 billion light years away. So we cheat, politely, with Einstein's permission. A galaxy cluster weighing a quadrillion suns bends the light behind it into a telescope built from gravity itself. No mirrors, no glass, just mass. In 2022, the trick delivered Earendel, a star at redshift 6.2 magnified more than 1,000-fold, the most magnified star ever seen. Reading it was like reading a candle's flame from across a continent. But Earendel is a hot blue B-type star inside a galaxy already salted with metals. Magnificent. Not our quarry. The lens works. The target still hides. Now, the part that concerns you. Every atom in you heavier than helium was forged inside a star. The carbon in your cells, the oxygen leaving your lungs as you watch this. That forging began somewhere in stars like these. You are downstream of the first bonfires. Their ash is your inheritance. In 2026, the hunt finally produced a name. Astronomers call it Hebe, a compact knot of light near GN Z11, a galaxy at redshift 10.6, and one of the most distant ever cataloged. When the universe was barely 4% of its present age, 480 million years after the Big Bang, This light set out on a journey of some 13 billion years. Hebe's spectrum hits the checklist. A helium line at 1,640 angstroms, equivalent with above 20 broader than ordinary stellar nurseries ever produce. Big hydrogen lines, nothing else. No carbon, no oxygen, a metal content below 2% of the sun's, the cleanest chemistry ever recorded at that depth. Still, we have been here before. In 2018, an antenna in the Australian desert called EDGE reported a radio trough twice as deep as every model allowed, and the textbooks trembled. 4 years later, a rival instrument named CERAS-3 went hunting the same signal and found silence. The miracle dissolved into static. So we say it plainly, candidate, not certificate. Hebe has survived sterner scrutiny, to be fair. High-resolution Webb spectroscopy confirmed the helium line after the initial medium-resolution claim. And an independent analysis weighed every rival reading. A cluster of up to 1 million solar masses of first-generation stars fits best, and a accreting black hole fits worst. The balance of evidence leans toward the monsters. Meanwhile, the ash trail warmed closer to home. NGC 1277. A fossil galaxy in our own cosmic neighborhood, carries a silicon surplus, matching what pair instability monsters are predicted to leave behind. Not the fire, the soot. After decades of chasing shadows through the dark ages, are we finally seeing smoke from the first fire? The hunt is going industrial. In the dry silence of South Africa's Karoo Desert, 350 radio dishes stand facing the same patch of sky, listening. The array is called HERA, and its target is the cosmic dawn itself, the moment the first star's light began warming the cold hydrogen that filled the young universe. Year after year, it stacks desert nights, hour upon hour, waiting for the signal to rise above the static. So far, silence. The team has published the strongest limits yet, which is a careful way of saying, not yet. The whisper is still quieter than the noise. Then, there is the ear being built in Western Australia. SKA-Low will field 131,072 antennas spread across the desert, more ears than a city has windows. Catching that same dawn is one of its headline jobs, and construction is already underway. Above them both, Spherix has been mapping the entire sky in infrared since March 2025. One forecast says its glow maps could hold the combined light of the first star's helium, not one monster, but all of them, shining together. And fully assembled, waiting for its rocket, sits the Roman Space Telescope. Launch is no earlier than late 2026. Its cameras will hunt the deaths themselves. First, stars torn apart by black holes, or blown apart whole. Here is what a confirmation would settle. The monster's true masses, the origin of the first black hole seeds, the bill for reionization, and who paid it. One spectrum would cache a century of theory. The eyes are nearly open. So take stock, one last time. A universe that began in darkness and stayed there for 100 million years. Monsters we have never seen, but can now describe their masses, their appetites, the 3 ways they could die. We know how big they grew and why they stopped. We know the menu of their deaths and the ashes each one leaves behind. Seeds of black holes, possibly already found, sitting too heavy and too early for any honest explanation. And a candidate named Hebe hanging in the archive, awaiting judgment. None of it is proven. All of it is described. A century ago, the Dark Ages were not even a rumor. No candidates, no seeds, no descriptions, nothing between the last light of the Big Bang and the first galaxies. Now that silence has a census, a crime scene, and a growing line of suspects. The telescopes are being built, the sky is being mapped, and the whisper is being chased from 3 continents at once. But some stories do not end with evidence. They end where they began. Go back to the first sky. Nothing glows. Nothing has ever glowed. For 100 million years, the universe holds its breath, then a spark. Every light since descends from it. The stars, the cities, the screen we are watching it on. All of it from one fire, lit in a universe that had never known flame. Its embers are only now reaching us, which leaves the oldest question we have. How do you light a universe that has never known light?